Good afternoon and welcome to Micrographics Fusion 360 Sheet Metal webinar. My name is Carl Van Roy and I'll be presenting today, and we are going to be looking at Fusion 360 Sheet Metal. What can it do? I'm an application engineer with Micrographics, and my email address, should you require it, is on the front screen here, the welcome screen that you should be seeing. Everyone will be on mute for the webinar. However, the chat panel is open for you to ask any questions. You can post them in there and I will either answer them as I see them, or I will cover them at the end during the Q&A session. So let's get started. Having a look at the agenda here, we'll start with a short intro into what sheet metal design is and where it is used. And then from there we will move on to explaining the rules surrounding sheet metal design, what features are available in the design environment, how to create a flat pattern of your design, and what this flat pattern is used for. And we will then look into creating 2D drawings of our part of that flat pattern. And lastly, a sneak peek at some new previews in Fusion 360 before closing with a summary and Q&A. Okay, so intro into sheet metal. Where is sheet metal used? Sheet metal is used widely in many products, both commercially and industrially. The easiest way to identify a sheet metal component is the fact that it's made of flat stock and has, for the most part, straight bends when we're looking specifically at Fusion 360. And the sheet metal design tools in Fusion 360 can be used to create these components. But you are not limited to using metal. Any component that can be made from flat stock, be it plastic or even cardboard, can be designed with Fusion 360's sheet metal features. Here in the picture we find a few examples of some shop fitting items made from plastics and cardboard, as well as some metal components. All of these items would have started out as flat stock and being cut and bent into shape. So these types of items are good examples or good candidates for sheet metal design. So for the intro, we will look at a high-level overview of the workflows within Fusion 360 for sheet metal design and processing. Basically, our first step within Fusion 360 would be to create your bent component using the sheet metal tools, which will be discussed in the next few slides. And then once you have created that bent component, you would then flatten it out to get what we call our flat pattern. This essentially describes the shape we need to cut from the flat stock. The flat pattern could be exported to a 2D DXF file for use. The flat pattern can be exported to a 2D DXF file or used to create a 2D drawing. Alternatively, Fusion 360's manufacturing workspace can be used to program for CNC cutting. Unfortunately, as with anything, there are rules to stick to, and in the next two slides we'll have a look at these rules when it comes to designing in sheet metal. So the rules, the first set of rules are going to do mainly with the geometry of the components being designed within Fusion 360. We'll see that Fusion 360 caters mostly for press break or contouring type operations, generally resulting in straight bends, as we see in the part on the right-hand side, or contoured lengths like corrugated roof sheeting or aluminium gutters. The material has to be of a uniform thickness, with no areas thicker or thinner than the specified sheet metal thickness. So bearing in mind, the components are made from that flat sheet stock, so we need to stick to that thickness. Another rule, the folded components or flat patterns themselves, the folded components or flat patterns cannot intersect themselves, as this makes it impossible to open up and flatten or cut respectively. So when designing, your folded component needs to be able to open up and flatten down, and once flattened, none of the parts of that can overlap in the flat pattern. With Fusion 360, you're limited to creating single-bodied sheet metal components. So for each component, sheet metal component you create, there can only be one single solid body and not multiples. And also, you cannot copy and paste sheet metal bodies. This would create more than one body, and this is done to honor the sheet metal rules for components and create a single flat pattern per component. If you had multiple bodies, then you would not be able to create one single flat pattern. It wouldn't know which body to create that flat pattern for. The second slide here of rules that we have are rules specifically within Fusion where you can specify values. And these rules here are within the sheet metal rule dialog box within the sheet metal ribbon. These specifically control how the geometry of the component works. In the image to the right, we see a few options, but we see quite a few options, but I'll summarize them as follows. The thickness, this will basically be the thickness of the flat stock used to create the component, and then the model must match this to successfully create a flat pattern. The K factor, this controls the strength of the material at the bends, controls the stretch of the material at the bends, and this will affect the final size of the flat pattern. So as you bend a component, as you bend material, it tends to stretch. This K factor will take that into account on the flat patterns. Bend conditions, these settings control the geometry at the bend, including the internal bend radius. And then corner conditions, this group of settings will control how the material is cut to create reliefs at the intersections of 2 or 3 bends. So we'll go into a demo here where we have a look specifically at those sheet metal rules. Let me go here into Fusion 360. I'm actually going to start a new blank design. And within Fusion 360, if you are in the design environment, you have the option, the sheet metal tab available to you. This is where we will find all our sheet metal specific commands. And on the modify panel, we have the sheet metal rules option available here to us. Opening that up will open up a list of sheet metal rules that are stored within the program. So we have our libraries of rules, and for each of these rules you can go in and you can modify the rule. So here I have a rule, stainless steel 304, 2 millimeter. I click the edit icon, little edit pencil there. I can edit the name, I can edit the thickness, K factor, the miter or seam gap, and we can see here we can expand, open, bend conditions, and we can change the values here as required. Now you'll see that there are multiple library items listed. You are quite easily able to edit each and every one of these, or alternatively use one of these rules as a base to create a new rule. So if you have already set up a stainless steel 304 rule, but you want to change and have a different thickness available, you're quite easily able to use the new rule icon to duplicate that existing rule and modify values as needed. So that is the sort of the sheet metal rules built into Inventor, and once you start creating components, you will actually have the rule listed on the left-hand side, and I'll show this in a later demo on where to access and make sure that this correct rule is applied. So going back to the presentation, if we want to have a look at moving on from the rules, we can look at what features are available in the sheet metal tab, and one of the most important of these would be the flange feature. I like to think of this as a multi-tool of sorts, as you can use it in more than one way to create various different shapes. The flange tool can be used to create flat faces. As you can see on the image there, just a simple flat face. It can be used to add a leg or flange to an existing flat face. That second image there shows the part has been bent with extra material added to it. You can also create a sketch with a contour, and then you're able to create essentially a rolled form or contour flange shape from that sketch. So we can see there the sketch would have described the bends, and then the flange gives it the length or depth of that part. And then lastly, if you have, you can add a new face to an existing flange, but have that existing flange and face intersect or extend and intersect at a point in space and have the bend applied. It's not very clear in the image here, but on the right hand side there you can see very faintly two sketch lines, and the flange is bent past those sketch lines to that intersection point. We'll see this in a demo coming up. We'll create some of these flange features. Another feature to highlight is the bend feature. This is very useful. What should I say? This can be used to add a bend across a component by specifying the position of the bend with a sketch line. This is especially useful for converting legacy flat patterns into 3D models for use in new designs. In the image on the right, we can see a face or a flange was created from an imported DXF, and from there a stationary face is then selected, and each of those lines across the part represents a bend line. Those bend lines are selected and the part is then bent on that bend line. You select the line and you would select the direction and angle of the bend, and that part is then bent in those positions. So the images here show a series of bends, and you can continue going through that component to bend each of those faces up. So that was a quick introduction into those features. We'll do a demo here looking at, or starting off with the flange function and looking at how those various flanges are created. So the first one, as mentioned, was to create basically a simple flat face. If I wanted to create a plate that was 100 by 100 wide, maybe it even has a round on the one end, able to draw out that profile, finish the sketch, and then from here use the flange option, select the various profiles, and that flange option will then thicken it to the specified thickness. Now, because this is the first sheet metal feature that's being added, we can then specify the sheet metal rule for this component. So if I want this to be a 1.6 aluminium sheet, I would go ahead and select that rule, and we can see that the preview then updates to show that new thickness. So if I go up to 5mm steel plate, that will thicken up. I'll choose the aluminium 1.6mm, click OK, and that generates that flange, that face flange, as I like to call it. From there, you're able to activate the flange command again and pick a straight edge on the model to then bend that edge. You can grab the arrow and pull the arrow to get an idea of where you're going. The arrow will set the length of the flange. Alternatively, you can type it in. So I'm going to go here with a 45mm flange, and I'm going to use the little ball to control the angle. Let's say we bend it at 65. In the dialog box here, we have some options for the flange. We're able to choose to bend across that entire edge, or we could create a bend that is centered with a symmetrical offset from either side. I'm going to set that distance to 30mm in from each side. It's OK, and Fusion will then bend that sheet up and add that extra material to create that flange. Alternatively, if I want to create a flange that is based off of a curved sketch or a sketch that has some, let's say, shape to it, I'm able to draw that curve in and then build onto that, or use the flange tool to create the geometry from that. I just need to quickly add some constraints in here to make sure that this will flatten out after the fact. And so there I have a sketch that represents the profile that I'm looking for. I'll use the flange tool then to select that sketch and choose how much material I want here coming off of that curve. Because I have the sheet metal rule selected, 1.6 millimeter thick aluminium, it knows to add that thickness onto that sketch. So I don't have to worry about sketching the thickness of the component. For the distance here, I'm just going to bring it out, let's say, by 50 millimeters. I'll hit OK, and that then adds that flange on. Double check my settings here. Okay, so that adds that flange on there, and then we can continue having a look at the last setting there, or the last option I covered was being able to connect an existing flange with a, let's say, with a new sketch. So once again, I'm going to sketch on that same side, and I'm going to draw in a flange off here in the distance. New sketch, and I'll create flange off of that and then select an existing edge on a model, and it's not liking my inputs here. Okay, so let me do this another way. Look here at creating that flange and linking it. Let's have a look here at doing this. I'm liking that curve there on the flange. So joys of doing these sorts of presentations live. And so if I create a sketch on the side of the part, and I want to now add a flange that is further away from that component, I'm able to select the edge of the component, and it will extend that existing flange out to meet the new flange that I'm creating. So it extends that out. If I go ahead and deselect the edge on the existing part, we can see what we have. I'll then pick the existing edge, and it extends those two flanges to meet and create the bend in the corner. From here, I could go, one last thing that I actually didn't have is a screenshot in the PowerPoint, is that you can quite easily add multiple flanges at once. If you bend them out, they will miter in the corner. Okay, so a quick little demo there of what the flange tool can do. The bend command, let's have a look here. The bend command, converting this file. If we look at the existing sketch here, was a DXF that was imported in, and we can quite easily go to create bend, select the center face as the stationary side, and then each line that you select as a bend will then bend that component up and create your completely bent 3D file. So we've quite easily taken an existing DXF which was imported using the insert DXF option, and then rebent that model up This is nice for getting legacy 2D data into three-dimensional models. Yeah, I'm going to jump back here into the demo. Now, we've created a couple of bend features using Flange and the bend command. But sometimes you need to add features when that model is flat. So we have an unfold command which allows you to flatten out a component. If you look on the right-hand side here, I have a simple plate that's bent. The unfold command allows you to flatten that out. You can see the stationary face selected in blue and the bend selected in green. This is useful for being able to add features like the hole in this plate, and that hole is placed over the bend in the component. And then once you refold that model, you then have a feature that crosses over that bend as if it was cut when the part was flat. So you are getting nice perpendicular cuts through the component. So the unfold rule is nice for being able to open it up, the model, flatten it out, add features, and then refold it. Another feature that we have in Fusion 360 is called is a convert option. And so what you can do is you can create more complex features using standard modeling techniques. However, you do need to remember to stick to those Fusion 360, those sort of sheet metal rules that were mentioned in the earlier slides. And once your components are done, you can then use a convert option to convert them into a sheet metal component. One of the caveats here is that you do need to have a flat surface that you can select for this to be able to work. So in the case of the cone shown here in the image, one of the portions of that cone is flat to allow it to then be converted and open up. So just to show a demo of those two commands, able to go look at, let's see, sorry, let's go back to this model here. If I want to flatten this out temporarily to be able to add something to the model, we can go to the modify command and choose the unfold feature, selecting a stationary face and then selecting a bend to unfold. I actually see this here is split in two bodies, so I'm going to go ahead and hide that one body. And this folds the part open, allowing you to then work within the unfolded component. So here I can create a sketch over that bend, and then I'm going to go ahead and use the extrude feature or command to cut through that surface. So the cut is perpendicular through the model. Once you're happy with what you have done, you can then use the refold faces command to fold that back up, and we see that those cuts are still perpendicular to those surfaces. Gives you a nice clean flat pattern after the fact to be able to laser cut or cut out. Then if we have a look specifically at the cone, I'll step through this workflow a little bit here to show how I achieved this, because a model like this would not be achievable with the standard sort of sheet metal tools available. So basically started off with a sketch that represented the bottom diameter of the cone, created a second sketch at the top of the cone to create the top diameter of the cone. We go ahead and switch these sketches on. And then a third sketch which represented the side of the cone as well as the central axis. That last sketch was then used to create a short flat surface your surface will later be used to convert this component into a sheet metal part. And from that short flat surface, a revolution was created. So the flat surface went to the left, clockwise, and then the revolution went from that split line to the right, anti-clockwise. Those two surfaces were then stitched together. Let me just switch that body on. And that stitch was then offset to the thickness of the material that was used to create the cone, or that will be used to create the cone. So in this case, I think I used quite a thick material, probably about 5 millimeters. And now with that material being offset, we're able to go to the Create panel and then convert to sheet metal. Now before I do that, I'll explain why I used the offset option here. So under your standard solid modeling, you can create a thicken or an offset. And what that does is it takes that surface and it gives it a uniform thickness. That's one of the rules mentioned earlier, that it has the same thickness throughout the part. So here we can see the thickness was 5 millimeters. And that enables us to then convert this to a sheet metal component by selecting that flat surface. It shows here thickness detected, 5 millimeters. I hit OK, and then that will allow me to create a flat pattern of this component. So if I go to modify, sorry, create, create flat pattern, we'll choose a stationary face, which will be that flat piece, hit OK, and it will then open up that component. So that will flatten that out and give you a flat shape that can be laser cut to then be rolled into the cone. Just another example here, see I'm doing pretty good on time, is creating multiple components within one assembly that meet together in a corner. So once again here, I'll roll the timeline back a little bit. I have two surface bodies that I created that have this perfect seam between them, and those two surface bodies are then modified with, let's say, fillets and any other commands to round them off nicely. These rounded corners will basically represent our bends within the sheet metal, and so you need to be sure here to make to ensure that your internal and external bend radii are set correctly here on those fillets, so that when you add your thickness, you are maintaining that constant thickness through the part. So here the two components are thickened, and we can see currently that these are two bodies within the model. They are at the moment still standard components, and they can then be converted into sheet metal components. So we'll see here that that one there has been converted. It is now a component, and the second one is also converted, and each of those can then be activated, and we can then continue with any other processes. So in actual fact, if I'll go here and convert this thickness detected 2 millimeters, I'm going to go stainless steel 304. Okay, sorry, they have converted it to a sheet metal component, and we can now get a flat pattern of that. So using some standard modeling techniques, I'm able to create more complex shapes. However, you do still need to adhere to those rules specified within the earlier portions of the presentation. Excuse me. So, okay. Okay, so once you have designed up your component and you are happy with your final design, it is then time to create your flat patterns. Now, additional features, so once you've created your flat pattern from that component, additional features can be modeled into it, such as registration marks for bending. I've seen in flat patterns where small little notches have been created at the bend lines to make it easier for an operator to line up the bends within the machines, within the press brake before bending. These features, however, that you add within the flat pattern do not update back into the folded part. So unlike using the unfold option to add features to your bent model, adding features to your flat patterns stay in the flat pattern. They do not update back to the folded part. Once you've created flat patterns, you are then able to use Fusion 360's manufacturing environment to generate a CNC program to cut the profile from your flat stock. So you're able to actually do your complete round trip from design to creating flat patterns to actually creating your CNC program and post-processing that out to your machine, all within Fusion 360. Or alternatively, if you have an external supplier that does your cutting and bending for you, you can generate a DXF file and send this on to that supplier so that they can manufacture. Over and above creating flat patterns, you're able to take that flat pattern and place it down onto a working drawing. So we see here on the right-hand side a drawing with the flat pattern of the component I bent up earlier, and that flat pattern has dimensioning and actually see I don't have the bend table on there, but you are able to provide this drawing as a reference for manufacturing. You'll have the dimensions as well as any notes, material, thickness, as well as bend tables. In the demo coming up, I'll show how to create this drawing, and we'll also add the bend table to the drawing. As part of the demo, we will also go through the preview functions. So I'll handle the entire sort of manufacturing side in one demo. The preview functions do need to be enabled in the preferences menu before you're able to use them and test them. The two preview functions that we're going to look at as part of the last demo for this would be the manufacturing working model. The manufacturing working model enables the ability to create a linked model for manufacturing where the designer or CNC programmer can freely modify the file to suit manufacturing without changing the original model. So this manufacturing model can then be used to create your CNC program. So often, as an example, I have found that programming a chamfer or a fillet can be problematic if it actually exists within the model. So the manufacturing working model allows the programmer to remove these features and make it easier to select profiles and edges for programming. And then as part of the manufacturing model, you're also able to arrange sheet components onto a work plane. So as part of the manufacturing model, you would be able to grab sheet components and say, okay, I want to arrange these onto a flat plane and fit them within a specific envelope. Unfortunately, it is limited at the moment. It cannot flatten components out and then arrange them. So this is as per the image on the right-hand side here. It works for components that are already flat rather than opening up bent components and then nesting them as you would. So Let's have a look. We had quite a few things there to look at. So we go back to this file over here. So this file started its life out as a DXF, which may have been a legacy DXF from days of where a company maybe worked in AutoCAD and manually drew out the flat patterns. Now using that DXF and the flange and bend options, we're able to recreate the 3D model from that. Now Fusion 360 would take into account the K-factor and bending rules and the bend dimensions, as well as adding in any reliefs. So what we could do here is we could either modify this by adding in any corner rounds. So let's go ahead and do some, let's say, simple filleting and modify the existing part. So updating that legacy component, adding some geometry to it. From there, a flat pattern can be created. And the way you do this is you would select the Create Flat Pattern option, select the face that will be the stationary face, and then you hit OK, and the rest of the model is unfolded from that stationary face. If a flat pattern already exists, you are warned that you would, tells you it already exists. It asks you if you want to activate the existing flat pattern. If there was not an existing flat pattern, it would just go ahead and create that flat pattern for you. So I'll hit OK to activate that flat pattern. It is automatically updated to show the changes, and from here within the flat pattern environment, you're able to then go ahead and, as I mentioned earlier, add features. So from here, I may want to add a couple of notches into the profile to allow for the operator who is actually bending up this component to then align it within the press brake. So I'm just drawing a series of 2mm circles. Finish that sketch and then extrude those down through the part to create a small little notch through the component. So here I have them in the flat pattern. If I finish the flat pattern and go back to the model, we see that we don't see those small little notches there. They are purely in the flat pattern. So if I activate the flat pattern again, you can see them here on the left-hand side. After creating the flat pattern, you have the option at the right-hand side here to export as a DXF. Essentially here, all you need to do is switch on or off the Convert Splines to Polylines options. Most of the time, your machines and programs for your machines prefer polylines, so I suggest enabling that and setting the tolerance. So how fine that polyline would be broken down into. Hit OK, and then you save your flat pattern as a DXF file. This can then be sent on to your supplier. Alternatively, you're able to go into Fusion's manufacturing environment, and at this point I am actually going to stick with this component, and in the manufacturing environment I'm able to create a setup for cutting, and that would be for laser cutting, and I can then choose, have a look here, I'll activate the flat pattern, activate the flat pattern and then create the setup. So here for the setup I will choose the cutting option, and for the model I will go ahead and select the flat pattern. Hit OK, and that then brings us into the CAM environment for programming the cutting for that flat pattern. I'm not going to go through the cam side of this. I just wanted to show that you can get through to that flat pattern to be able to cut the cam, or to be able to create the cam, the program for cutting that. I do have a setup one here. Let me just have a look. Okay, I'm not going to go into that one. So that would be just for a single component, flattening it out, taking it into the manufacturing environment. Alternatively, if you have an assembly made up of multiple flat parts, you're able to follow a similar workflow where you go into the manufacturing environment. And in this case, I already have a manufacturing model created, so it has taken me directly to that. What I'm going to do here is I am going to go ahead and switch that one off and enable the, what I'm going to go ahead here and do is, there is the original model. I just ghosted out. I'm going to right click and create a manufacturing model. And that brings in my original model. And I now have a manufacturing model that I can modify and change for manufacturing. So what I'm able to do here is go ahead and right click on that manufacturing model and choose edit model. Takes me to a edit manufacturing model environment where you are then able to do things like remove features. You're able to remove specific faces. You can replace complex shapes with primitives. You can even do things like press, pull, add fillets, shell. So various options here for solid and surface modeling. Specifically, what I want to look at today is the ability to modify this and arrange the items. So by choosing the arrange option, I'm able to go ahead and select these components, and as I'm selecting them, you'll notice there's an arrow pointing off of the surface or off the face. That will be the face that points upwards when you arrange it. So all my A-side surfaces. So I'm going to pick all the surfaces on the outside of this box, and those objects are going to then be arranged. Now, what do we arrange them onto? You're able to arrange these onto an existing plane or sketch. I don't have a sketch here, so what I'm going to do is I'm going to pick a work plane. And because I don't have a sketch, I then need to specify the size of, let's say, plate I want to put these onto. So if I try to put this onto a 1.2 by 1 meter plate, that will then update and fit those components onto a plate. If that plate is too small, I will receive an error. It tells me all those components cannot fit onto that plate. You're able to set spacing of the parts from border spacing, so from the border of the plate to your part, and then item separation is essentially the spacing between components. So if I know I have a really accurate laser, I can squeeze these parts closer, say 1 millimeter. That will update and bring these components closer. Once hitting OK, that manufacturing model is created. I can finish edit, and from here create a new setup for cutting, as I did previously, and then select out of the manufacturing model drop-down either the default model, or I can choose one of my manufacturing models that I have created. So I'm going to pick the new one I created, hit OK. No model selected, all models solid will be used. Okay, so it's using all 1, 2, 3, 4, 5 components for my machining because I didn't go here at the model and pick which ones I wanted to cut. So I'm cutting all of them, and I now have my component set up ready to cut out of a single sheet. Okay. So in summary, after that quick whirlwind tour of sheet metal, Fusion 360 gives you a set of sheet metal tools that enables you to create parts or components that are made from flat stock. And that flat stock, as I mentioned, could be metal, plastic, cardboard. I have seen guys designing flat sheet metal or sheet metal components out of hardboard for laser cutting and creating gift boxes, that sort of thing. Within Fusion 360, you're able to export DXF files for manufacture. Alternatively, you are able to import DXF to be able to create the design. And there is the ability to do drawing creation for clarity and extra instruction, which I'm realizing now I didn't show in the demo. So what I will do is I will quickly go back to that, and let's have a look at this component here and go back to the design. And what we can do is we can activate the flat pattern. Actually, we don't need to even activate the flat pattern. What we can do is we can go File, New Drawing from Design. And it picks up that the model here is a flat pattern, so we can do a drawing for the folded, or as a sheet part. So we could do the drawing for the folded model or the flat pattern. So you can choose which one you want to include in the drawing. So I'll go with the flat pattern, leave the default settings for now, and that opens up that part and puts its flat pattern down onto a drawing. And so here we are. I can change the scale as needed, put that down on the drawing, and from there we can see that the flat pattern brings the notches in. We can add things like a hole table quite quickly and easily, with its whole ID notes being placed automatically onto the bins. And from there you can add your standard dimensions and notes as required. So that is quite nice for being able to give it to the person manufacturing so that they have better clarity on how to manufacture. And then once again, to finish off the summary, that manufacturing workspace where you are able to create the toolpaths and also the manufacturing model with the arrange option to be able to essentially do some very simple nesting from within Inventor. I quite like this arrange feature for the fact that it promises better things in the future. It's a nice start to getting nesting into Fusion 360. That is the basically quick summary of that sheet metal tools within Fusion 360. And what we'll do is we'll move on to a Q&A session. We have a few minutes left in the session. And I haven't seen any questions come through on the chat panel. But, I will give a few minutes now for any questions. Okay, thank you, Conrad. Now, if you have any questions, if you do come up with any questions after playing a bit more with Fusion, you're more welcome to contact one of our officers. My email was also on the first slide. We will be posting up the video on YouTube, on our YouTube channel as well. So look for Micrographics South Africa. And my email address was on the first slide of the presentation. So yeah, I hope you have a bit of fun playing with Fusion 360 and working on the sheet metal. Okay, thank you for attending the webinar. There are no other questions, so thank you very much for attending.